Hello everyone. In this class we are going to discuss about the physical properties of haloalkanes and haloarenes. Let's start. First we are going to discuss about the physical state, color and odor. Alkyl halides are colorless when pure. Okay. Alkyl halides are the colorless compounds which are not very in the presence of the pure condition. But bromides, iodides are develop color when exposed to the light. What is going to happen? It's going to change their color. Why? Because due to the oxidation with the air. Okay. Next, up to carbon 8 are colorless liquids. Okay, up to carbon 8 member chain elements compounds are going to be colorless liquid in nature. Okay, higher means higher than the carbon 8, higher than the carbon 8 members are colorless solids. Okay, the more than the carbon 8 are going to be colorless solid ones. Okay, the molecules which are going to having the more than carbon 8 chain which are going to be colorless solid in nature. These are the physical state of these compounds. Okay, next let's see the solubility. Okay, what do you mean by solubility? The amount of solvent is going to dissolve the solute. That's going to be solubility. Let's see the solubility. Haloalkanes are polar. Definitely, they are going to be polar in nature. How it is going to be polar? Let's see by this diagram. Okay, what do you mean this? Okay, this is the substituted methane. It's going to be X means anahemi halogen element. Here delta minus and it will be delta plus. That means it's going to show the polar in nature. Haloalkanes are polar in nature. That's why they are slightly soluble. Why they are slightly soluble? Because they are slightly polar. That's why this means delta minus and delta plus means that small percentage of negativity and small percentage of positivity is going to be present on the molecule. That's why they are slightly soluble. Okay, because they are not having the permanently charged. It's not going to permanently negative. It's not going to have the permanently positive charge. Okay, these are highly soluble in organic solvents. Okay, even though they are having the slight polar nature, they are going to be soluble in the organic solvents like alcohol, ether, benzene, THF, and carbon tetrachloride. These are to be known as of organic solvents. Let's see the density. Okay, if you pour in the any container, if it's going to be sink up or is going to be float. Let's say alkyl bromides and iodides. The bromides and iodides are heavier than the water. They are heavier than the water. Okay, this is going to be density variation. And fluorides and chlorides are lighter than the water. They are lighter than the water. This is going to be change in the density. Okay. Okay. Next one, the melting point and the boiling point. Okay. Okay. But there is a series iodide, bromides, and chlorides and fluorides with respective derivatives. Okay. It is due to why it's going to happen is due to the size of the halogen element. Okay, why is going to iodine is having the high melting and boiling? It is due to the high bigger in the size. You know that from fluorine to iodine, the size is going to be increase. Okay, due to the increase in the size. Even though there is increase size, there will be an increase in the van der Waals forces of attraction. High in the case of the iodine is going to gradually decreases from iodine to fluorine. Which one is van der Waals force of attraction? This increase the boiling point. This increase the boiling. What are the 2 points? The size of the halogen element and the increase in the van der Waals force. These are the 2 conditions to increase the boiling point of an molecule. Okay, next one. The boiling point increases with increase in the number of halogen elements. If an element is going to having more than one, it's going to having the high boiling point. Why? Because there will be an increase in the first one is the sign, second is the van der Waals force of attraction. Okay, let's see the order. First one is tetra substituted halogen element, next tri substituted, di substituted, and mono halogen substituted complex is present. Why? Because they are having the high number of chlorine substituted elements were present. That's why it's going having the high boiling point, and least in the case of the chloromethane. Okay, the boiling point decreases. The boiling point decreases with the increase in the branching. Okay, why it's going to be decrease? That's it. The boiling point decreases due to increase in the branching. What is going to happen in the branching case? The branching makes the molecule more compact and decreases the surface area. Decreases the surface area. If I take any paper, okay. If I take any paper, okay, there is some paper is here. Okay, it's going to it's going to cover the large surface area. If I fold it up, okay, if I fold it up, now it's going to having the more compact and decrease the surface area. Now this surface area has been decreased. Why? Because I fold it up. Okay, that's why if any molecule is having the longer chain, if any molecule having the longer chain, it's going to having the large surface area. If any molecule having the branching structure, is going to having the decrease in the surface area. The surface area is going to be decreased in the case of the branching molecule. The surface area is going to increase in the case of the long chain alkyl halides. Okay, due to the decrease in the surface area, the boiling point is going to be decreased. If any molecule is having more branching, that is going to having the low boiling point. Any molecule which is having the large branching is going to having the low boiling point. Okay, if I see the relation, the surface area is directly proportional to the boiling point. If any molecule having the high surface area, there will be least high surface area means is going to having the least boiling point. If any molecule having the least surface area, is going to having the high boiling point. The more the branching, the lower the boiling point. Okay, let's see. Next, if you understand this topic, let's try to solve this. There's a question. So what is the question? Check the boiling point order. It's going to ask you what is the order of the boiling point of this. Okay, let me read it for you. Tertiary butyl bromide, normal butyl bromide, isobutyl bromide. We already know which one is more branched and which one is least branched. We already know that normal butyl bromide means it's going to having the normal butyl bromide. It's going to having the 4 carbon chain. Okay, it's going to happening like this. Okay, it's going to happen. Simply it's going to having like this. Okay, let's see. Butyl, okay, is going to be normal. Normal means we are going to put together bromide. Okay, it's going to be satisfy this CH2, CH2, CH2. Okay, this is the normal butyl bromide. It's going to be a longer chain, means it's going to having the large surface area. It's going to having the large surface area means it's going to having the large boiling point. If any molecule having the least surface area, is going to having the least boiling point. Okay, the butyl bromide is going to having the least boiling point, and the normal butyl bromide is having the high boiling point. I think not understood. Okay, next the boiling point. Next, that's going to be continued for part. The boiling point of a haloalkanes increases with increase in the size of alkyl groups. Here, alkyl groups means the chain. Okay, the carbon chain. If the carbon chain is increases, the boiling point is going to be increase. If any molecule having the larger the chain number is going to be higher, the boiling point is going to be higher. If you see the CH3, CH2 twice Cl, CH3, CH2 twice Cl, CH3, CH2 Cl, CH3 Cl. You can see that it's going to first one is going to having the longer carbon chain. That's why it's going to having the high boiling point. The chloromethane is going to having the least carbon chain. That's why it's going to having the least boiling point. Okay. Next is the haloarenes. Boiling points of isomeric dihalobenzenes. Of any molecule is having to be substituted either in the case of the same halogen compounds, if it is isomeric dihaloates, it will ask ortho position or in the meta position or in the para position. What's going to happen in the dihalogens? Okay, they are going to be having the nearly same. Okay, the molecules which are having the isomeric dihalogen benzenes are going to be nearly same, but their melting point, observe the point. I'm going to explain this one in the next slide. The melting point is going to vary like this. Para position is going to having the high melting point, and ortho and meta position isomeric dihalide benzene are going to be nearby the same. Okay, why it's going to happening in the case? Why in the case of para is more? Why it is less in the case of the? Why it is similar in the case of ortho and meta positioned complexes? Okay, it is due to the it's a symmetry. It's due to the symmetry case. That's why they are going to be varying. Okay, let's see. Okay, as I said, the example is going to be as follows. Okay, it's going to be isomeric dihalo substituted benzene is present. This one is which type of? This is going to be having to be known as is going to be ortho. Ortho 1, 2 chlorobenzene, dichlorobenzene. This one is 1, 2, 3, 1, 3 dichlorobenzene, and this one is 1, 4 dichlorobenzene. Disubstituted benzenes were present. These are the iso DPC names, and this one, the ortho position is going to be orthochlorobenzene, and this one is metachlorobenzene, and this one is parachlorobenzene. Okay, these are the common name of these complexes. Okay, let's see its melting point and the boiling point comparison. Okay, I have given the data here. Boiling point means from the 453 Kelvin, 446 Kelvin, and 448 Kelvin. Let's see the melting point: 256 Kelvin, 249 Kelvin, and last one is 323 Kelvin temperature. The temperature is given here in the form of in the Kelvin rate. Okay, given the temperature in the Kelvin rate, I am going to be given in this case. Or the given data, I am going to paste it in here. Okay. Okay. What about this one? This one is to be ortho positioned complex. This one is meta positioned complex, and this one is para positioned complex. I think you got this. Let's check the boiling point area, which is going to have the high boiling point. Let's see. Either it's going to be ortho, meta, or para. Okay. The ortho positioned isomeric diamond is going to be having 453 Kelvin. That's with the highest boiling point. Okay. The ortho positioned isomeric diamond is having the highest boiling points. Next one is 446 Kelvin and 448. The first one is ortho. Next one is para. Next one is meta position. Okay. In the case of the boiling point, not the melting point. Let's see the melting point first. The melting point is going to having the ortho position is having the 500 and 256 Kelvin, and meta position is going to having 249 Kelvin, and para position the isomeric diamond is going to having the 323 Kelvin. Why? Because it's going to having the symmetrical differences. Due to the symmetrical differences, they are going to having the variable temperature. They are having the variable boiling point and the melting point. Okay, I think we got this. Okay, in the next class we are going to discuss about the chemical properties of the haloalkanes and the haloarenes.